So the next thing we want to do now is find the expression for inductance L. So we're going to find the inductance L. We have a solenoid. Let's define some terms here. So let's say we have a solenoid. Our solenoid has length L. It has, length is usually a lowercase l. We'll leave it as lowercase l so it matches the book. Let's say it's carrying current I. And it has the total number of N coils. For our picture here, just so we get an idea of what the magnetic field looks like, let's say that the current is going up in the back and down in the front. It's a little bit hard to picture with that kind of a drawing, so I grabbed a slinky. So let's say this is our solenoid, our inductor. Let's say it's coming up in the back and down in the front. We know that the magnetic field comes down through the center of the solenoid. The direction of the magnetic field, we put our thumb in the direction of current, so it's going down in the front. We ask, what do our fingers do? Our fingers are coming out and pointing to the right. So if our current comes down this way, the magnetic field comes out that way. So the magnetic field in this solenoid, you get by your right hand rule, points this way. One thing we know is that the magnetic field of a solenoid of length L with current I and the number of coils equals N is the strength of that magnetic field is mu naught, permeability of free space, 4 pi times 10 to the minus 7 Tesla's meters over amps, times the number of coils times the current divided by the length. That was a result we found using Ampere's law. So there's the expression for the magnetic field of a solenoid. So we said we're going to try and find the expression for inductance. Let's write down our definition of inductance. Inductance has a symbol L, and it's equal to the net magnetic flux through the solenoid divided by the current through the solenoid. So phi m, let's make sure we understand what that is the total magnetic flux through solenoid. How do we find what that is? Well, let's think about how we find magnetic flux. The total magnetic flux would be the total magnetic flux through each coil added up. So our net magnetic flux, phi m, is the total flux. Since it's the flux through each coil added up, it's N times the flux of only one coil. So if we can write down what the flux through one coil is, we multiply by N to get the total amount of flux. So our flux through one coil is equal to B times the area. A is the area of a single coil. That's just B times our area is pi times R squared. So then that tells us that our total magnetic flux is N times B times R squared. Well, B is the magnetic field in the solenoid. We know what that is. So then we can write this down. We can simplify just a tiny bit. We've got mu naught times N squared times I times pi R squared over the length L. So there's our net magnetic flux through the coil. We can put this in our expression for inductance. And it gives us an expression for the inductance. We see that we have an I on top and an I on the bottom. So those I's cancel. there's the inductance of a coil in a circuit where our coil has length L, number of turns N. So that gives us the total inductance. Next, we're going to ask some questions about how it responds in the circuit. What is the potential? That's the next question we're going to get into, so we'll think about that next.